Here there are 3 circles with dots in this diagram. Now, when you have a circle with a current involved, they're talking about a wire that either goes into the page or comes out of the page. So just to explain what's happening in this diagram, I'll try to draw it here in 3 dimensions. Okay. They got a circle and a dot, and a circle and a dot, and another circle and a dot. Okay, what it represents, though, is wires that are protruding out of the page. Okay, because we're trying to represent 3 dimensions with just 2, is the idea. And what the dot means is that the current is coming out of the page toward you. So just imagine that. So we have current I, and I. All right. Now, any current carrying wire is going to create a magnetic field around it. So we want to find the field strength at point A, which is a point over here. Now, one of the things we can do is we can use the right-hand corkscrew rule, which says point your thumb in the direction that the current is going, and then grab hold of the wire with your fingers, like that. Okay. As you can see, the field lines will now form concentric circles that wrap in the direction of the fingers. So what we can do is take that first wire and make it the center of a circle that would travel through point A, and it would have this type of counterclockwise magnetic field. Okay, and it would keep going, of course. But we don't really care about what's happening over here on the right. We just care about what's happening at point A. Now, we can see that the contribution at point A due to this wire would be directed downward. So you want to draw a vector that's tangent to that circle. And let's give each of these wires a number. Like the one on the top can be I1, this one can be I2, and this can be I3. So this is wire 1, wire 2, and wire 3. All right, so that's one contribution, and I'm going to call it B3 because that contribution came from wire 3. But now we should do the right-hand corkscrew rule for the other wires as well. So what they're going to end up doing is they're going to make these concentric circles, and that's going to give us a field directed this way, which I'll call B1 because it was due to wire 1. And then you just want to do the same thing for wire 2. we'll get something that looks like this, and that can be B2. So it just requires thinking about what type of vectors each of the different wires would create. So that's our result then. We're going to have a contribution from wire 3 called B3. We'll have a contribution from, we'll have a contribution from wire 1, which is B1, and then a contribution from wire 2. Now we just have to get the magnitudes of each of those. So we have the formula that the B of a wire, it'll be mu naught I over 2 pi d. Now d just refers to the distance from point A to the wire that's exerting the magnetic field. So with this problem, you gotta find some of those distances with geometry and trig and such. So this distance here will be d1, the distance from point A to wire 1. This can be d2, and then d3 is actually going to be a very long distance here. So we want to find each of those distances. Let's see if we can find d1 just with some Pythagorean theorem. It says in the instructions that A is 1.25 centimeters. And we want to find that distance D. So D is going to be the square root of this. Comes out to 0.0177. All right, so that's also going to be D2, just by symmetry. D3, however, will be 3 times A, which is 3 times 0.0125 meters, 0.0375 meters. All right, now find the B total at point A. So one option would be to find each magnitude. So do this, and then attach a direction to it as well. So for B1, we see that it's got a standard position angle of 315 degrees because it's pointing in quadrant 4. And B2, though, has a standard position angle of 225. So if I do B1 first, then what I can do is I can include the directional information like this. Cosine of 315I plus sine 315J. That's all you need in order to take care of the directional information. So see, the left side of the expression takes care of the magnitude. So this is the magnitude. And this right part of it is all directional information. Does that make sense? Yeah, the right side is all directional information. And that takes care of the contribution due to wire 1. But now we want to include wire 2. And we'll just do the same thing. But use its standard position angle. Okay. So this is all for the field due to wire 2. All right, and then we need one more. We see that B3 is pointed directly downward, though. So that's going to be an angle of 270 degrees. And so for that, I don't even really need to include cosine 270 because it's going to be 0. Okay. Now we just want to add all those up. Interestingly, we can see that the x components are going to cancel with each other. So we don't even really need those. And we know that cosine of 270 is 0, so we don't even need that. All right, so I'll just plug in the numbers. The current is 2.46 amps for every wire. Okay. As we can see, the contributions from wire 1 and 2 are actually stronger magnetic fields than the contribution from wire 3. That's not surprising because wire 3 was much farther away than the others. All right, I think I'm getting 5.25 times 10 to the minus 5 Teslas, negative j hat